In the real world, data rarely comes perfectly balanced. Whether you're working in healthcare, manufacturing, security, or wildlife conservation, certain classes naturally occur much less frequently than others. Let me give you some concrete examples. In medical diagnosis, healthy tissue images vastly outnumber cancerous ones, but missing that rare cancer case could be life-threatening. Manufacturing defect detection faces a similar challenge when most products roll off the assembly line perfectly fine, with defects appearing in less than 1% of cases. Security surveillance systems must sift through footage where normal activities dominate, while suspicious events are incredibly rare but critical to detect. Wildlife monitoring presents another classic case where common species like pigeons appear in thousands of images, while endangered species might only show up in a handful of photos. When you train a model on imbalanced data, something counterintuitive happens. The model can achieve seemingly impressive accuracy, say 95%, by simply learning to predict the majority class most of the time. But here's the catch. It completely fails at detecting the minority class that you actually care about. In our animal dataset example, we have dogs, butterflies, and squirrels. Dogs appear frequently in our photographers' daily captures. Squirrels are much rarer. A model trained on this raw data might get really good at spotting dogs, but completely miss squirrels, which defeats the purpose if you're trying to monitor rare wildlife populations. The model isn't broken. It's doing exactly what it was trained to do, optimized for overall accuracy. But in the real world, failing to detect that rare defect, missing that medical condition, or overlooking that security threat can have serious consequences. Class imbalance can be addressed through several effective methodologies, each with distinct advantages and limitations. Engineers often combine these approaches to maximize their effectiveness, and understanding these techniques helps us appreciate why our auto-balancing solution is so powerful. Undersampling or downsampling reduces the number of samples in the majority class to match or better balance with the minority class. This approach helps to prevent the model from being biased towards the majority class, though it may discard potentially useful information from the majority class that could have helped in defining decision boundaries. Oversampling or upsampling increases the number of samples in the minority class by duplicating existing instances or creating synthetic ones. This technique preserves all majority class information while balancing the dataset, but can potentially lead to overfitting if exact duplicates are used. This is because the model might memorize specific minority class examples rather than learning generalizable patterns. SMOTE, or synthetic minority oversampling technique, creates synthetic examples for the minority class by interpolating between existing minority samples rather than simply duplicating them. It works by selecting a minority class instance and its k-nearest neighbors, then creating new instances along the lines connecting these points. This approach helps to avoid overfitting while expanding the minority class representation in the feature space. Other methods require adjusting the loss function and other hyperparameters, which can become quite complicated. This is where Datature's class balancing feature comes in. Instead of leaving you to manually figure out complex upsampling ratios or wrestle with hyperparameter tuning, our auto-balancing algorithm combines the best aspects of these traditional approaches while eliminating their drawbacks. To enable this feature in your workflow, click on the dataset block and toggle the Enable Class Auto-Balancing option. A pop-up will be displayed showing the current distribution of classes in your dataset. Notice how skewed our animal dataset is. Dogs dominate with 60% representation, butterflies have a moderate 30%, while poor squirrels are severely underrepresented at just 10%. Click on the Auto Balance Classes button at the bottom left. The chart updates to show a much more balanced representation that is optimized given your dataset's constraints. Then, click Confirm to save this setting. We can make this even more powerful by combining the balancing with augmentations. This is crucial because simply duplicating rare samples could lead to overfitting. The model might memorize specific squirrel images rather than learn generalizable squirrel features. With augmentations enabled, each upsampled image gets randomly transformed, be it rotations, color adjustments, or lighting changes. This creates meaningful variations that help your model become more robust to real-world conditions while maintaining the balanced class representation. In our experiments, the impact was dramatic. Our squirrel class, the most underrepresented, saw a 32% improvement in F1 score. But here's what's really interesting. Even our majority class, which is dogs, improved, going from 85% to 94% F1 score. This shows that balanced training doesn't just help minority classes, it creates better models overall. This means that in real-life applications, you're not just catching more rare events, you're building more reliable, robust AI systems across the board. Try out our class balancing feature on Datature Nexus today and see how addressing this fundamental challenge can transform your model's real-world performance.